So hello guys, welcome back again to another video. So in this video we are going to talk about SN1, SN2 and E1, E2 mechanisms. So we are going to talk about the mechanisms and we are going to talk about how each mechanism changes when the substrate, nucleophile, solvent and temperature varies. And also we are going to look into the problems, how we can solve a problem, how we can approach a problem. Likewise, and after these basic points, I'm intended to fill this chart. This is a summary of whole 4 mechanisms, so you may have a good advantage from this chart. So let's see. So first let's move into each of these mechanisms and let's see how each one of mechanism operate, right? So how these thing operate in our chemical environment. So first let's talk about the SN1 and SN2 mechanisms. So let me take this white color. Okay, no, that's not the color. Okay. SN1 and SN2 mechanism. So first let's talk about the SN1 mechanism, right? So in this case, here's the thing what happened. I'm going to take a molecule just like this. Let's take R1, R2, R3, and here we have X. This X is the leaving group, right? In SN1 mechanism, first step, okay, the first step is the leaving of this leaving group. So this leaving group will be leaved on its own. So you will have a carbocation. You have R1, R2 and R3. This is a carbocation. And the next step, what happens is, here you have your nucleophile. This nucleophile come and attack to your carbocation. So in the final product, you will have this one, R1, R2, R3, and here you have nucleophile. You can see this X, right? This X group is been replaced by your nucleophile. This is a replacement. So that's why we are calling this as substitution. Here S stands for substitution, N is stand for nucleophilic reaction. So what is this 1 means? The number 1, what does that mean? So if you look at your rate expression, right, you know in your basic kinetics, the rate expression is based on the rate limiting step. So what is the rate limiting step on this particular mechanism? You have 2 steps. This is the step number 1. This is the step number 2. So how we can identify the step 1 and step number 2? So basically, like in general organic chemistry, you will be given what is the rate determining step. But either way, you need to be aware of how to determine the rate determining step. Let's take this step number 2. Let's take step number 2. So in general case, right? In general case, you can see there's a carbocation. The carbocation is being attacked by a nucleophile, and you will have a neutral compound. This is a carbocation, right? This is a charged compound. Here you have a neutral compound. So a charged unstable compound is being converted into a neutral compound. So this step is rapid, right? Because these molecules are like to be neutral. So this charged representation is somewhat unstable. So this step is rapid. This is a rapid step. So here you can see the neutral compound, the stable neutral compound is being converted into a charged one. This is particularly a little bit unstable. So this one is slow. Why? This neutral compound is going to be unstable or charged species. So this is the slow. This is the slow reaction. So now how we can write the rate expression? You have rate constant and there's only one component here, which is the substrate. So only the substrate's concentration will determine the rate of your overall reaction. So if you take the overall order of the reaction, what is the order? Order is 1, right? That's represented in this number. This is the first order reaction. SN1 means substitution first order reaction. So you can sense it, right? If you see a SN1, which means only one species is there in the rate determining step, which means this one, right? So there are some another few important points in substitution reactions, so SN1 mechanism, right? First one is this rate remaining, this rate constant, and the other one is, look at this look at this step, right? You can see this carbocation is a planar, right? This carbocation is a planar one. So if I draw the 3D structure, here you have the carbon, here you have R, just think like a 3D structure, right? So here in the upside and downside there are two vacant positions. These are occupied by R groups. The upside and downside have a vacant positions. So this nucleophile can either attack from this side or this side, right? What happens if nucleophile attack from this side? This nucleophile will bonded with carbon like this, and because of this nucleophile's electron cloud, this R group will be repelled to this side. What if the nucleophile attack from here? Then it will form a bond like this, and its electron cloud will repel the R groups on this side, right? You sense it, right? Okay. Now based on these two orientations, the initial configuration can be changed. I hope you know about the configuration with that R and S. So if you know about these R groups, you can check whether this molecule is R or L. So not L, S. Right. So the final product can be either R or S, because there are two ways, right? There are two ways to bind to our original carbon. Let's as an example, let's say our initial molecule is R. Okay, our initial molecule is in R configuration. So if our nucleophile attack like this, right, you can see nucleophile is now attached to this kind of position. You can see it's the same position as our leaving group. So this is stays R. But what if our nucleophile attack from the other direction? And then what happens? This nucleophile will be attached from this place. The configuration is changed. Now it's S. This can be happening in SN1 mechanism. Why? Because in the first step there are two vacant sites. So our nucleophile can attack in two directions. So in this case I will write it, configuration can be changed. Okay. So I hope it's okay, right? I hope it's fine. So let me erase this one. And let's look into the SN2 mechanisms. Okay. Now in the SN2 mechanism, what happens is, let's take SN2 mechanism. So let's take a molecule like this, R1, R2, R3. Here you have your leaving group. Now in S2 mechanism, right, this leaving group won't be lived on its own, right? This one won't go on its own. The nucleophile needs to be attacked first. Here you have your nucleophile. Now nucleophile will attack to your carbon first. Due to this attack, this leaving group will be removed, right? So this leaving group has no intention on leaving the carbon atom at initial case. This nucleophile is the one who's pushing this leaving group away. So you will have in a transition state like this, R1, R2, R3, and a half broken XC bond and half formed nucleophile carbon bond. This is the transition state, right? This is the transition state. So through this transition state, you will have your final step, your final product, carbon. So let me take another color. Carbon, R1, R3, R2, and here you have the nucleophile. So this is a one-step reaction, right? This is a one-step reaction. This is the reactions intermediate. So this is a one-step reaction. So there are no problem with identify the rate determinant step. There's only one step. So this is the rate determinant step. So if you write the rate expression, you can see there are two components involving in the steps. So your rate expression should be like this: nucleophile concentration and substrate. So if I ask you what is the order, order is 2, right? Here you have first order, and overall order of the reaction is 2, which shows you on this particular number. So some people like misunderstand this, like the number represent the number of steps of the mechanism. No, it's not represent the number of steps, it represents the order, right? This is the order. So you can see in SN1 mechanism, it's first order reaction, only the substrate is involved. In SN2 mechanism, it's second order, both substrate and nucleophile both are involving in our reaction. And just let's look at the configuration. What about the configuration? Would you say? Let's say this is R. If I ask you a question like, can this compound be R? No, right? Because you can see for nucleophile, here you have the nucleophile. There's only one way to attack for nucleophile. This nucleophile cannot attack from here because there's a leaving group. This leaving group contains an electron cloud. When nucleophile come through in this direction, our leaving group's electron cloud will repel this. The only possible way to this nucleophile to achieve is through here. So to bonded with carbon, there's only one position to this nucleophile has. It's the opposite direction of X. So if your initial molecule is R, then definitely your final product will be S. The retention of configuration will be achieved in this case. So configuration will be changed. Right? I hope you understand that. Now these are the basic mechanism for SN1 and SN2. So now we need to talk about like there are 4 components in this mechanism which are affecting the mechanism, right? So let's look at it like this. The first one is the substrate. Okay, let's talk about the substrate. So in this case, you know, these are normal like methane, primary alkenes, alkanes, and sorry, primary alkyl halides, and here you have a okay. So sorry, I just misspelled it. So this is basically that CH3X now. So here you have a primary alkyl halide, and then you have secondary alkyl halides, and then you have tertiary alkyl halides, right? These are the possible orientations with these alkyl halides can achieve, right? So let's assume this is a halide, right? Just go with that direction. So what I want to tell you is, let's say you have a tertiary alkyl halide like this. So basically your substrate is a bulky group, right? Here you have carbon, then you have R groups here, and here you have the X. So what mechanism would you prefer to go with this bulky group? You can say these are bulky groups, right? These are bulky groups. So in SN2 mechanism, you can see the nucleophile has to go through these components, go through these parts. So it's really hard if you have these kind of bulky groups. So SN2 mechanisms won't prefer this kind of bulky groups. SN2 mechanism would be preferred a primary alkyl or this kind of very simple molecules, because nucleophile can achieve to this carbon. It can reach this carbon very easily through this, because there are no that much strong electron field around these small molecules. So here also this primary alkyl, there are possible paths to connect with this carbon. But when you have tertiary alkyl halides, you can see your path is being blocked through these electron fields. So what happens is, when we are talking about primary, secondary and tertiary, SN2 mechanism would prefer primary alkyl halides, and also secondary is also somewhat fine. So however bulky groups are not favoring the SN2 mechanism. Why? Because in SN2 mechanism, you can see the nucleophile has to go through these components. So if you have a bulky groups, it will reject this nucleophile. Let's look at SN1 mechanism. In SN1 mechanism, right, you can see like it happens after the nucleophile is attacking after the carbocation is formed, right? After the carbocation is formed, so it's completely fine for it. There is no retention that much effective of the bulky groups. Why? Because anyway, when this carbocation is formed, there are two vacant positions. Here this is carbon, and here you have two vacant position. No matter it doesn't matter the bulkiness. So this SN1 mechanism, right, you can see it prefers tertiary and secondary. It doesn't that much prefer the primary alkyl. Why is that? So you know, in your basic organic chemistry, when the carbocation is formed, right, this carbocation is formed, if you have a tertiary carbocation, it has higher stability. These alkyl parts, it can donate its electron density towards your carbon center, which can neutralize this positive charge. I hope you know about these things, right? Just basic things. Otherwise, if you have no idea about it, it's okay, right? Just know the fact for it. Just know that point. Okay, here you can see when you have a tertiary, let's say like this, you have carbon, CH3, these are alkyl groups. So when you have a tertiary carbocation, these methyl groups can donate its electron density towards your carbon center. So this positive charge, so electron density means the negative charges, no? So when negative charges are coming towards your carbon center, this positive charge is going to be diminished. So your overall compound is going to be close to neutral. So when your carbocation is reducing is that charged ability, you are going to increase the stability. So basically neutral compounds are more stable than the charged one. So when you decrease this positive charge, it becomes more and more neutral, so your stability increases. So that's why SN1 mechanism prefers tertiary ones. So it can stabilize the carbocation. In primary ones, right, the stabilization is not that efficient like tertiary. So in SN1 mechanism, you would see tertiary or secondary structures are preferred. So let's put it on our table. So for SN1 mechanism, tertiary or secondary structures are preferred, right? Which means bulky groups are okay. Bulky groups are okay. When it comes to SN2 mechanism, right? SN2 mechanism, if you remember, this is the SN2 mechanism. So now you can see the bulky groups are not preferred. So primary and secondary. So bulky groups are not preferred. Are not okay. Now the substrate is okay. I hope you get the idea about the substrate. Now let's move on with the next one, which is the nucleophile. Let's see what happens with the nucleophile. Okay, so let's move on to the SN2 mechanism. You can see the SN2 mechanism starts with the attacking of this nucleophile. Right? SN2 mechanism starts with the attacking of this nucleophile. So strong nucleophiles are better for SN2 mechanisms. Okay, strong nucleophiles are better for strong nucleophiles are better for SN2 mechanism, because this nucleophile has to start the mechanisms. This is the one who has to start the reaction. So in SN2 mechanism, strong nucleophiles are preferred. So now what are nucleophiles? Let's talk a little bit about nucleophiles. What are nucleophiles? Basically, the nucleophiles are like, you know what are the nucleophiles mean, right? So here you have a chlorine minus, these are nucleophiles, right? OH2, basically water, these are nucleophiles. So in most cases, right, basicity parallels nucleophilicity, right? Which means higher the basicity, like if you take a higher base like OH minus, these are overall good nucleophiles. This is the most case, but there are specific positions where there are specific points where basicity is not parallel to nucleophilicity. When the bulkiness come into your compound, right? When the bulkiness comes into your compound, you know, like if I take an example like this, let's say CH2 CH2 CH3, and here you have C2H5, and here you have C2H5, and then here you have O negative. So this is a bulky group, right? This is a bulky group. So I would say this is a good base. This is a good base, but this is not a good nucleophile. This is a bad nucleophile. This is a bad nucleophile. So I wanted to understand that the basicity mostly parallels nucleosity. If you have a higher strong base, which means a strong nucleosity, but if your base affected by this bulkiness or steric hindrance, then it changes. More bulkier it gets, it's okay for the base, but it's not good for the nucleophile. Why is that? Here, look at this. So the nucleophile is basically the one who's attacking for the electrophilic position, right? So in this case, you can see when nucleophile, in order to nucleophile to be good, it should attack to this carbon. But if this nucleophile gets more and more bulkier, it's really hard to go through these components, right? The electrostatic interaction will be stopping them. So that's why that's the case. So you need to understand, in most cases, basicity parallels nucleosity, but only one here you can see when the bulkiness or the steric hindrance comes to place, this condition won't accept. More bulkier it gets, it's a good base, but it's a bad nucleophile. That's the case. I hope you understand my point, right? So in these cases also, the SN2 mechanism, which means it's a strong nucleophile. It needs a strong nucleophile. Okay, strong nucleophile. So less bulkier, strong nucleophile. So strong nucleophiles is needed. So here you can see in SN1 mechanism, for rate determining step, you have no effect on nucleophile. So mostly we say this needed weak nucleophiles. Weak nucleophiles are okay. So overall, right? Overall, for substitution reaction, you need to understand your nucleophile has to reach into your carbon center, right? The nucleophile has to reach into the carbon center. So for substitution reactions, your nucleophile should be less bulkier. If your nucleophile is much more bulky, if it has much more steric hindrance, then there's a problem. Why? It cannot reach into the carbon center through these other components. This will reject it. These are having electron cloud also. So if your nucleophile is much more bigger, then these electron clouds will repel your nucleophile, right? You need to understand that. So you need to have a strong nucleophile but less bulkier. Okay, so let's add it to our table. So when it comes to the nucleophile, right? So For SN1 mechanism, nucleophile has no effect. So weak nucleophiles are okay. For SN2 reactions, strong nucleophiles are needed. Strong nucleophiles are needed. So for both of these cases, this nucleophile has to be less bulkier. Right? Less bulky nucleophiles. And now let's talk about the solvent. So let's talk about the solvent. Okay. Now there are two types of solvents. You need to understand there are two types of solvents. First is polar protic. Another one is the polar aprotic. Okay. So basically the polar protic means, right, solvents that can form hydrogen bonds, right, that can affect with hydrogen bond, like H2O, CH3, OH, and these kind of things, right? These are polar protic, like CH3, CH2OH, and let's take CH3, COOH. These guys, these are polar protic, right? There are hydrogen oxygen bonds, OH bonds, there are OH bonds. These are the polar protic ones. The polar aprotic means they doesn't contain any hydrogen, this hydrogen oxygen bonds, this hydrogen oxygen bond formation, right? Like DMF, so DMSO. So basically these are much more polar, these are less polar, right? These are much polar, these are less polar. So DMSO and DMA, these guys are polar aprotic. And finally you have non-polar. You know what the non-polar compounds are, right? So benzene, hexane, likewise these guys. Okay, so these are highly polar, these are middle, these are non-polar. So let's see how these solvents can affect our mechanism. First let's take the SN2 mechanism. So in SN2 mechanism there's only one reaction, right? There's only one reaction. Look at your nucleophile. Now in order to proceed with our SN2 mechanism, you need this nucleophile to attack faster, right? Faster the nucleophile attacks, sooner the reaction happens. So if you introduce a polar solvent, polar protic solvent, right? If you introduce a polar protic solvent, what happens is polar protic solvents are ionic. No, they can stabilize your nucleophile. They can stabilize your nucleophile. So like here you have your nucleophile. Now you have a polar protic solvent. Now your solvent will trap your nucleophile and will not let it move like this. It will form bonds with your nucleophile. So now your nucleophile cannot move, right? This is not what we want. We want this nucleophile to move quickly and attack here. So by introducing a polar protic solvents, right, you cannot achieve this higher efficiency. So in order to quickly let this nucleophile to attack, you need to introduce polar aprotic solvents. So polar protic solvents won't be work here. Polar protic solvents are the one who much more suitable for SN2 mechanism, because it's not going to stabilize this nucleophile. It will push nucleophile away, and so nucleophile will go and attack to our carbon. But in this case, look at this, right? Our nucleophile has no effect on this, right? Our nucleophile has no effect on this. So you can see in our rate determining step, our final product is the carbocation, right? Our final product is a carbocation. So if we can stabilize your carbocation, right? If you can stabilize your carbocation, which means this reaction is much more likely to be happen because your final step is much more stabilized. So reaction will do faster, reaction will happen faster to get to obtain that stabilized final form. So in this case, by introducing a polar protic solvent, right, here polar protic solvent, which are basically that like H2O. These polar protic solvents, they can stabilize your final this intermediate product. So in SN1 mechanism, the polar protic solvents are the one which are much suitable. So let's put it down here also. So for SN1 mechanism, right, SN1 mechanism, the carbocation is forming. So you need to stabilize the carbocation, you need polar protic, just like H2O, methanol, likewise these guys. For SN2, you have no charged species are forming, so like you don't have to think about that, but you need your nucleophile to attack faster. So if you introduce a polar protic solvent, what happens is it will stabilize the nucleophile, so your nucleophile cannot move. So the polar protic solvents won't be worked on SN2, but it will work on polar aprotic solvents or non-polar solvents. So just like DMSO, what we have to here, DMSO, DMA, DMF, these guys. Okay, so these are the effect from the solvent. So final thing is the temperature, right? The final thing is the temperature. So temperature, basically the temperature, I will just tell you, like the temperature, you need low temperatures. You need low temperatures for substitution reactions. For elimination, you need high temperatures. Right? So you need low temperatures for substitution reactions. Okay, now let's move into the elimination reactions. Okay, elimination reactions. So first, let's look at the E1 mechanism. Okay, just like in our substitution reactions, I hope you now, if I ask you a question like what does 1 means, this number 1 means, I think you can answer it, right? This 1 means is the first order reaction. Okay, so if I take a molecule like this, let's say we have a hydrogen, and here you have a R group, carbon, hydrogen, and here you have a leaving group and another R group. Okay, so in this case, what happens, just like in the substitution reaction, the first step is removal of our leaving group. The leaving group will be removed on its own. So here you have R, C, H, you have R, carbon, hydrogen. So our leaving group is been removed. Okay, now you have a nucleophile, or mostly in these elimination reactions we call this nucleophile as a base, as I have introduced you before. This nucleophile and the base, these two are mostly, in most cases they both act as the same, right? Like there's only one difference in one occasion, like that's a bulkiness. So when the bulkiness comes into the place, that's how the nucleophile and the bases are going to be changed. Otherwise these both are changed. So I will put a base on this case. So I will put base. So I will put a base like this. Okay, just this is just like a nucleophile, right? The same function. This is a nucleophile. So in this case, right, in elimination reactions, this base won't go and attack to this carbon. No, it will go and attack to this hydrogen. Now this base will attack to this hydrogen. So this one will be broken to here to form the alkene. Here we have our final product. So if I ask you what is the rate determining step, I think you can do it, right? You can see in first step the charged species is forming. The charged species is forming on the first step. The charged species are relatively unstable. So in first step, the neutral stabilized compound is going towards the unstabilized compound. So this reaction is not that much like a good reaction, like it's not that much moving forward. So this is very slow. So in this second reaction, you can see unstabilized charged molecule is going towards a neutral stabilized molecule. So these guys are loving it. These guys are very like to go into a neutral state. So this is rapid. So now you can see this is the predetermined step. So if I write the rate expression, you can say K, and there is only one component here, which is the substrate. Just like the SN1 mechanism, right? Just like the SN1 mechanism. So here you have the substrate. So if I talk about those 4 points here we have, which we are talking about: substrate, nucleophile, solvent, and temperature. Okay. So first the substrate. Okay. In the first the substrate, you can see then nucleophile or our base is not initially there, right? So basically for E1 mechanism, same like the SN1 mechanism, tertiary or secondary, these guys are preferable. So like the bulkiness is okay for E1 mechanism, right? Bulkiness is relatively okay. So when it comes to the okay, so and then if we talk about, so let me put it there first. So here you have tertiary and secondary, right? Bulkiness is completely relatively okay bulkiness. When you talk about the nucleophile or base in this case, yeah, the base in this case, you can see for our predetermined step, the base has no effect, right? So basically, so most oftenly, a weak base would be preferred. Weak base would be preferred here because the base has no effect here, right? Base has no effect here. The weak base is preferred. So let me put it in here. Weak base. Now in this case, you can see the difference, right? Here in our substitution reactions, we have been told that our nucleophile should be less bulkier. Less bulky our compound is, it's more like to be a nucleophile, right? It's more like to be a nucleophile. So if you come up with a nucleophile with much more bulkiness, right? If you have come up with like this one, let's say C5H8, somewhat like that, and again C5H8, C5H8, and here you have oxygen, and this is a one compound, and here you have CH3, CH3 hydrogen O minus, right? These are two nucleophiles, right? So what my question is, if I ask you to do a substitution reaction, what nucleophile would you use? Definitely this one, right? Here you can see for this nucleophile, it's less bulkier, so it's easy to penetrate our carbon cation. So less bulk here it is, it's more nucleophile. This is much more bulkier. This is much more bulkier. So I have told you this is a good base, but not a good nucleophile. So you can, if you see in your question paper, if you see a much more bulky nucleophile, right? Much more bulky nucleophile, it's better to go with elimination reactions, because elimination reactions love bulky groups or base. Bulky bases are very preferred here, right? But these are not like to be bulky. So when we talk about the solvent, same like our substitution reactions, right? You can see we have a positive charged species over here. So with the polar protic solvent, which means like H2O, CH3OH, likewise these hydrogen bonding solvents, these guys can stabilize your product. So in this case, let me put it here. Polar protic solvents are preferred. And for temperature, I have told you, like higher temperature is preferred for elimination reaction, because you are breaking the bonds, right? You are breaking the bonds, so temperature is needed, higher temperature. So let's move on to the E2 mechanism. Okay, for E2 mechanism, just like the SN2 mechanism. So in this case, let's take a compound like this one. You have a R, and here you have C. Let's take another H and another R and X. So in E2 mechanism, you can see this leaving group is not leaving on its own. You need to help it, right? So you're going to introduce a base, So I have told you that the base, nucleophile, both are the same in most cases. Only when the bulkiness is introduced, then it's changing, right? So in elimination reactions, these bases or these guys are not considered about this carbon, right? They have nothing to do with this carbon. They are going for hydrogens. So due to this attack, this bond will be broken here. Now due to this repellment, our leaving group will be left. So it will be left. Sorry about my grammar. So here you have R, C, double bonded C, H, and you have R and here R. So this is a one-step reaction. So you can draw the transition state for this too, right? Just if I draw the transition state, it should be like this. So let me take a blue color. Here I am drawing the transition state. Now this bond is halfway broken, and here it has halfway formed the bond with our base. So here a half formed bond is there and halfway broken bond with our leaving group. This is our intermediate or like transition state. Okay, so this is the E2 mechanism, right? This is the E2 mechanism. So what are the points of E2 mechanism? You can see if I talk about the rate, okay, there are two components. You have the base and you have the substrate. Okay, so this is a second order reaction. So that's why this 2 means it's a second order reaction. So let's talk about the effects of that 4 compounds, right? First thing is the substrate. So most commonly, like as I have told in our SN2 reactions, this base has to attack first. So like we would say it's more good to have primary or secondary, but it's okay to be tertiary, right? You can understand, right? So this base has nothing to do with this inner circle, right? It just need to touch this hydrogen. That's all. So even though this contains much more bulky groups, it doesn't mind. So most of the time, elimination reactions, right? For elimination reactions, all these 3, primary, secondary, tertiary, all these are preferred. It's completely fine with elimination reactions. So in this case, I will write here tertiary, secondary, and yeah, primary is also fine. So in this case also primary is also fine, right? So like if your question is asking to determine whether the reaction is elimination or substitution, then it's better not to look at the substrate, because you cannot much tell about the substrate. You can tell a huge difference from a nucleophile, right? In here also you can see, in this case here, the base is the one has to attack first. So you need to have a strong base. You need to have a strong base. So I will put it here. You need to have a strong base, right? Which means bulkiness is okay for here. But you can see the bulkiness is not okay for substitution reactions. If you see a strong base with like much more bulkiness, it will definitely go for elimination, right? We will do some example, right? Then you can understand easily how we can apply these things in our real questions. So for now, I need you to understand this. Like if your question is asking to check, like to determine whether the reaction is substitution or elimination, you cannot tell it with the substrate, because eliminations are like they support everything. But you can tell it very mostly you can tell it by nucleophile and solvent also. So when it comes to solvent, you can see, so base is the one first attacking here, right? So if you use a polar protic solvent, which means that like H2O, these guys are going to be stabilize our base, so it's not going to work. So you need polar aprotic solvents here. Polar aprotic solvents, which means like DMSO, DMS, DMF, DMSO, like these guys. So here like H2O, ETOH, like these guys. So and just like the same temperature is higher temperature is possible. So like when you are doing the questions, right? When you are doing the questions, always target these things: nucleophile and substrate. These sides are important, right? Don't look at the temperature initially, right? Look at the temperature at final step. Temperature is not that much important. Temperature is important, right? Yeah, high temperatures facilitate the elimination reactions, but it's not always do that, right? If you have a very good bulky group, let's say you have a very bulky nucleophile, right? Very bulky nucleophile. So it's a very bulky nucleophile, but you are giving a high temperature. But with a very bulky nucleophile, right? You cannot go with substitution. Not at all. You cannot go with substitution. Let me tell you an example. Here, look at this. You have a carbon. Here you have a C5H5, and here you have a bromine atom, and here you have a chlorine atom, and here you have a let's say there's a living group. Okay, now you are adding this guy. Okay, you are adding this guy C5H5. Here you have C5H5, C5H5. Okay, C5H5. So but you are using, let's say 20 Celsius. So this is very cold, right? Very low temperature. So if you look at the temperature and determine, see, like if you look at the okay, yes, there is a hydrogen over here, no? So it's possible to do elimination reactions, right? So there's a carbon here, so there's a possibility for elimination reactions. So if you look at the temperature and initially say, okay, this is low temperature, which means this is had to be substitution reaction. No, it's wrong, right? You can see this is a bulky group. Your base, your nucleophile is a very bulky group. So I have told you that nucleophile and the basicity is parallel. But when it comes to the bulkiness, right? Basicity increases, nucleophility down. So this is a good base, not a nucleophile, which means it goes for the elimination. So this should be elimination, right? Elimination, it should be, and it also should be E2 elimination. Should be E2 elimination because this is a very good base. It's a very good base. So I hope you get the idea about it, right? You get the idea about it. So these are the things you need to understand. So we will do the questions and practice problem in our next video. Until then, I need you to understand these core concepts. These are very important. So I hope you are okay with this chart. So we will meet it in our next video about when we are talking about questions.